Hello, I'm Mark LeMay, and I'm going to talk about the extended abstract we submitted titled Gradual Correctness, a Dynamically Bidirectional Full Spectrum Dependent Type Theory. So why are we doing all that? Well, first of all, dependent types are great. Here's a little contrived program in Agda that shows off some of their features. We have a length index list and a rep function that will repeat some number of times and create a list of that length. We have a head function that knows that a non-empty list can always extract the first element of that list. And we can put together in a computation where we dynamically feed 1 plus x into the repeat function and extract the first element. And all of this type checks, and it's great. But there's one problem. If we swap x plus 1 and 1 plus x, then we get this error from Agda because we don't know that 1 plus x is equal to x plus 1. Essentially, equality is hard in dependent type theory. I'm sure this isn't surprising to anyone who's done any serious work there. But does it have to be so hard? Here's the programming language we're working on. I've included some things you might find in, say, the standard library of Agda. And we can do the same function as before. And if we run this function using the Agda style type checking, we'll get our version of that error, which says that x plus 1 is not obviously equal to 1 plus x. But if we use our intended style of type checking, everything's fine. And we can run the function and type check it and whatever we would like to do. So the obvious question is, what happens if we have something that isn't actually equal? So here we have a function that is that gives the wrong length at every input. And if we try this function, we get this type error, which says exactly why these two types are not equal, and exactly what values they're not equal at, where the error is. And finally, we have what may be more of a realistic scenario, where we have an addition where we're using a function that's almost correct. It's right at every single input except 1. And we can use this function as much as we like until we hit the 1 input where there's an error, and then we can deduce that when you add 1 plus 1 with this bad add function, it actually returns 0 instead of 2. What we're trying to do is give good dynamic errors instead of maybe questionably good static errors. And the static errors can still be warnings. That would probably be useful. So we're not actually losing anything as far as correctness would be concerned. We're just letting you run more programs. This was kind of our goal starting out, but it turns out that this project can be viewed in a couple different ways that might be more or less interesting depending on which areas of dependent type theory you work in. So another way of thinking about this is we're delaying the equality check of bidirectional type checking until runtime, or that we're gradualizing in the sense of gradual type theory, just the equality proofs of extensional type theory. Or we have a new approach to handle the albeit simple effect of errors without a handle. So before we get started, we should just make sure we understand some of the limitations of the system. The system is not logically sound. It is designed to be a programming language first, not a theorem prover first. That means we're allowing things that would be probably useful to programmers, but probably not good for logicians, such as unrestricted recursion, type and type, and our prototype handles unrestricted data. We are more restrictive than gradual types, where gradual types allow you to put any untyped term anywhere. We insist that you put enough type annotations that we can at least tell what you're trying to do, even though they don't necessarily need to be correct. Our implementation in our write-up contains some thoughts on user-defined data, and we're still kind of reworking how we're handling that. Quick overview of the technical content. We have a surface language, which you just saw. It elaborates to a cast language, and then we've proven some properties about the cast language and about the system itself. So the properties we've proven about the cast language is that it has a weakened version of type soundness, where in regular type soundness, well-typed programs won't get stuck. In the cast language, well-cast programs don't get stuck without a witness of inequality. We have a couple of gradual guarantee-like properties of the whole system. Every type elaborated into the cast language is well cast. Every term typed in the surface system elaborates. Blame never points to something. So we'll never get an error from something that was well typed in the surface language. And evaluation is consistent with what you would expect. So let's review the theoretical surface language first. It's a full spectrum dependently typed language with unrestricted recursion type and type. It has its own type system, so we can compare this as a baseline. That's bidirectional. It has type soundness. It is logically unsound, as I mentioned before. And if you run it and call by value, we believe that there's a partial correctness that you'll still be able to rely on. The syntax is pretty simple, and the only things worth pointing out are that we embed the source locations directly into the syntax for static or dynamic errors, and we have an annotation for types that's familiar to people who do bidirectional type checking. And then our typing rules are similarly standard. And we're using the arrows over the type symbol so that you can see which direction the information flows. And this is similar to a lot of prior work going all the way back to Martin Loeff's first attempt at the dependent type theory, which turned out to be unsound. And various people, especially Cardelli, have studied it since. So what do we do if a user makes a term that's reasonable, possibly, but doesn't type check in the surface language? Then we encode enough information that our cast language can find an error if it exists. So our cast language is almost exactly like the surface language, except all possible problematic things are drawn into one cast syntax that contains the underlying type, the location that asserted the two types are equal, an observation that evolves over the evaluation of a cast term, and the type that it thinks it's going to be. So for instance, if we want to claim 7 is a bool, that's fine as long as we know the underlying type of 7 is nat, and we have a location where the user has tried to do use 7 as a bool, and an observation that records how that term was evaluated. This seems simple, but this is dependent type, so nothing's so straightforward. We had to solve several problems to make this reasonable. First of all, we had to figure out what to do when casts made their way into types themselves. For instance, what's the interpretation of a list of length true? Casts can simply block evaluation. 7 is not actually applied directly to F here, 7 is applied to the cast. And worst of all, equality for type terms is not decidable. So we can't simply hold on to an expression and then check that it is exactly equal to another expression. We solve the first issue by separating evaluation and blame and allowing this kind of evaluation to get stuck. Then the blame judgment can extract errors from stuck terms, and we don't need to commit to an interpretation of this problematic term. We keep eliminators from being blocked by casts by adding additional evaluation rules. Specifically, inspired by contract monitors, we bring 7 under the cast with a new cast that switches the argument input. So in order for this to work in this example, 7 can be applied directly to F as long as we now think that 7 is a bool. We'll get around equality being undecidable by limiting ourselves to blaming things that have exactly different constructors. The statics of the cast system assert these properties, and you can see here we have a type system. We call the type system for the cast language a cast system just to differentiate it from the other type systems we may be using. And it is pretty standard as far as that goes. The dynamics are less standard. We need to extend our notion of value so that the casts are sufficiently evaluated. We add small step rules for the casts, as you can see in the second rule there. And we have a new blame judgment that will extract inequalities of constructors from terms. Now, often you see errors treated directly in the small step semantics, but separating it out into a separate blame judgment makes many things quite a bit easier and allows us to have different levels of aggressiveness in our error catching. So finally, we prove the cast language is cast sound. A well-cast program will not get stuck without a witness of equality. This is similar to the proof of type soundness, except we need to extend the computation to casts. Blame and values and small steps are extended as shown. And a lot of the canonical form lemmas are modified to allow blame. We have this proven in Cox, so you can check that out if you want the details. It is a minimal version of cast soundness in that the minimal amount of error checking is allowed. In our prototype, we check things more aggressively. Finally, we have our elaboration procedure, which takes possibly untyped surface language terms and converts them into the cast language. Elaboration accepts almost all untyped terms, but there are some untyped terms that will not elaborate. This is because we're using bidirectional typing, so we need to know what type is intended, and if not enough type information is given, we can't figure that out. So for instance, if we know the type of a function, we can tell that we're using 7 as a bool here in the first example. But if we simply have lambda x to x, we do not know what type x is supposed to be, so we will not be able to elaborate it. Elaboration will always return well types, well cast terms, with the appropriate static information inserted. Here are the rules for the elaboration procedure. You can see that it follows very closely the bidirectional typing judgments of the surface language. We have proven several properties about elaboration, that every term that's elaborated in the cast language is well cast. Terms that type in the surface language will always elaborate. Terms that typed in the surface language will not be blamed. And elaborated terms will have consistent evaluation with the unelaborated terms. So we're still working on this project. And currently we're trying to get data in a more usable state. Data is a little interesting because when you have type and type dependent functions, recursion, you can simulate church encodings and calculus of construction encodings, and you can simulate large elimination and induction. So in theory, you don't actually need a formalization of data since all that computation is already available to you. However, this is really hard to use, and it doesn't provide the good errors we would like. It's hard to inspect into a church encoded data and assume and have that error mean anything. So for implementation and in our write-up, we implemented a form of dependent eliminators. Unfortunately, these are still kind of hard to use in practice, and it complicates the theory in ways that are not ideal. So we're currently in the process of reworking data elimination into something more like dependent pattern matching. So far, our tests show that it's much easier to use this, and hopefully we'll have a cleaner theory. Additionally, once that's done, we hope to add a layer of automated testing so that the difference between type checking and our runtime checking is more academic. For instance, if you do something obviously wrong, well, and we'll probably uncover stupid mistakes most of the time. We want to polish the implementation. For instance, it would be very nice to turn traditional static errors into nice warnings and get the error text and warning text a little cleaner. And finally, we have probably a unique opportunity to do user studies here because we have almost exactly the same implementation with one specific feature turned on and off. And we could probably throw this at some undergrads and see if they actually find this helpful. Thanks for listening. If you have any questions, I'd love to hear them. You can check out our implementation on GitHub, and excited to hear what you have to say.